Uh, Hello, my name is Adrian Mosquera. I'm from Spain, from Santiago de Compostela. I'm a hematologist, believe it or not, because of what I'm going to tell you in the following slides. But we do our research line about AI applications, artificial applications for personalized medicine in myeloma. And you know, when you are a hematologist working on computer science and you get invited to a dinner, dinners. Well, you don't really get invited to many dinners if you do this. But if you look at, you tell people you work in computer science, you will see the blood coming out of their face. You know, like, oh my God, why it was me in my only free night. No? So this is probably a very disruptive field, which will probably give us a lot of information in the future on how to optimize treatment in our patients. And I'm here not to promote your knowledge about AI, but I hope that after this talk you can become active supporters of advanced data analytics within clinical trials for myeloma and other disorders. So I hope I can move my slides. These are my disclosures. And of course, you've heard a lot about the applications of big data and AI in every field of society, particularly strong in the financial markets, but this is progressively translating to every part of our society. And obviously, medicine is not an exception in this sense. So what do we have particularly important in our field, in the oncology and hematology fields about the application of AI is related to a guidance by the FDA in 2019, where the FDA recommended 3 steps to enrich clinical trials with 3 kinds of approaches that are all data-driven and that can be used in the near future, implemented somehow with AI tools. The first point refers to the reduction of population heterogeneity in clinical trials using biomarker combinations or biomarker selections to confirm that the population is homogeneous. The second point is prognostic enrichment, selecting populations of patients who are an unmet medical need and where your study will give an evaluation of value for the patients. This is important because, for example, we don't have a stable definition of high-risk multiple myeloma. If you look at the trials, they are defining high-risk multiple myeloma patients differently. There is no consensus about whether plasma cell leukemia is or not a kind of myeloma. So there is a lot of debate about how we define a prognostic groups, and then this also translates in the results of the trials. And the last point refers to predictive enrichment, and that is to identify patients who have physiological characteristics, mostly genomic characteristics, or that make them more likely to respond, at least a priori, to the treatment that we are evaluating. So AI is referred to any device, any mathematical system that has the capacity of perceiving its environment somehow and taking actions to maximize the probability of achieving its objectives. And it refers to systems that simulate human cognitive activities such as learning and problem solving. And the big field of AI that we use is machine learning. Machine learning is when we when we develop algorithms that make statistical models for a particular purpose without the need for prior instructions by a human. Okay, so these algorithms do pattern searching and inference of this new data into new cohorts of patients. And the big picture of machine learning in this moment is this. We have 3 big groups: supervised learning, unsupervised learning, and reinforcement learning. Probably the most important one for our purpose is supervised learning, followed by unsupervised learning, and we will discuss 2 approximations to multiple myeloma that we have done in the past years relating to these different kinds of systems. In supervised learning, we know what we want to predict. We have either a classification or a continuous variable, and we want to predict how the patient will behave, or which is the value that the patient will have, for example, in terms of survival, or on terms of MRD negativity. In the case of unsupervised learning, we deal with situations where we have a lot of data, but this data is unlabeled. We suspect that there are different structures in the data, but we can't identify which are these structures because these are high dimensional and our brain can do that. So they allow us to identify clusters of patients, mostly with genomic data, that can be used for prognostication or drug response prediction. So when coming to survival, these are two nice examples of two machine learning algorithms that have been developed to predict survival in AML and CLL. And the nice thing is that, as you can see here, well, actually I can't point, sorry. But you can see that the algorithm take the same set of prognostic variables for each patient, but the value, the importance of these variables, these prognostic variables, changes according to the structure or the multidimensional scenario where the patient is. So the value of a TP53 mutation might be different depending on the other variables that on the value of the other prognostic variables, which is obviously totally expected, but we were not taking this into account. So for one patient, the predictions will be very based on a few of the variables, for example, beta-2 microglobulin, and others, the genomic profile might be more important. So when trying to face with myeloma and artificial intelligence, our main two ideas were that the treatment landscape is very complex, as you all know, and that risk stratification is suboptimal. And indeed, there are data indicating that, for example, the ISS and the revised ISS do not behave somehow better. The revised ISS is not somehow better in terms of C-index, of concordance index, than the ISS. And this is a problem because we need cohorts or systems that perform better in terms of individual predictability. So, of course, there are some examples, previous examples, that suggest that there is a role for predictive medicine, for the development of predictive algorithms in multiple myeloma that can help us to better risk stratify these patients or to identify signatures that characterize responding patients to different treatment schemes. And with this idea, we took the data developed by the Multiple Myeloma Research Foundation, who kindly shared the data with us, and we developed a machine learning model to improve prognostication. At least this was our first intention. So we took the data, we trained a machine learning algorithm, a random forest algorithm in particular, with gene expression data and with clinical variables. We reduced the dimensionality, and this algorithm was finally based on 50 variables, mostly gene expression variables, but also obviously some other important features such as age, ISS, beta-2 microglobulin therapy, or the first line of therapy. I mean, we selected these variables in an unbiased approach. So these variables were important for the survival prediction. And we created a nice prognostic score that can even give a personalized survival curve of expected survival for each patient with a high concordance index of 0.82. But the nice thing is that we had the first line of therapy into the model. So we reasoned that the model could just simulate the survival of all the patients with any of the 6 available upfront treatments in COMPASS. And then we could compare how patients who were treated with the optimal drug scheme, without the physician, the dermatologist even knowing it, how they behaved in real life. Did they survive more according to the prediction of the algorithm, or did they have the same outcome? And therefore, there is no hypothesis to believe that we can do actual predictive models in the context of myeloma treatment. So here you can see the survival curves. This is overall survival, by the way. The survival curves of patients treated with the optimal treatment scheme or any other suboptimal scheme. And as you can see, The blue line represents the survival of patients who were treated with the optimal scheme, and the red line indicates the survival of patients treated with any other scheme with a hazard ratio of 0.1 in the training set and 0.2 in the test set. And this was particularly relevant among patients treated with upfront VRD. So we could identify that patients treated with upfront VRD who have the prediction to be the optimal treatment, this scheme was very good, whereas those patients treated with VRD who were more candidates to KRD, for example, performed poorly. And this was independent of other possible confounders such as age, high-risk cytogenetics, transplant intention or not. So this is probably the kind of evidence that, actually retrospective evidence that we need to support its implementation into clinical trials. And indeed, we have recently compared the gene expression compartment of this predictor with that of the UM70, the University of Arkansas score, and we've observed a better performance in terms of both overall survival and progression-free survival performance in the data of their trials, that they shared this data, and we could compare the results, and actually it looks a better risk stratification system than the UM70 score. So it seems likely that we can use these models to optimize treatment in multiple myeloma, and this has to be implemented into the context of clinical trials. Actually, we are implementing this in the CARTITUDE-6 trial in order to guess who are the patients who will have the best response to the CAR T-cell therapy over the autologous stem cell transplantation. And the other approach that we used was based on very simple data from the Spanish group of myeloma from 3 different clinical trials. Of course, gene expression is complex. You can do it anywhere, and you need something that is easy to use. So this is another research line that we performed, and we took some simple information from these 3 clinical trials, mostly clinical cytogenetics and hemogram variables. And we use this kind of unsupervised machine learning algorithm, which is named Gaussian mixture model infitted by an expectation maximization algorithm. It's really complex to say, of course, but the idea is that when you have various variables, you can identify if there are latent variables that explain the distribution of these variables in the multiphases compartment. And in this case scenario, it's quite simple. We can all see that there are 2 groups of patients here, but life is complex. And when you grow with multiple dimensions, there are multiple groups of patients, and it's impossible to guess who are these patients. So using the same kind of data as that I mentioned previously in the Spanish myeloma trials, we trained a model to identify what's the optimal distribution of patients according to their prognostic situation. So are these 3 groups, 4 groups of patients, 5 groups of prognostic patients, prognostic groups, in the myeloma, in newly diagnosed multiple myeloma. And we actually discovered, to our surprise, that the optimal solution according to the prognostic system is 2. 2 groups perform better in terms of concordance index than the ISS and the revised ISS in all trials. The only trial where the results were similar were in the first one, but this has overfitting for the revised ISS because it was used to train also the revised ISS score. In the other 2 groups, you can see clear separations of the graphs. And what the model did, well, these are the curves in terms of overall survival and PFS, but what the model did to our surprise, and this was totally unblindly to us, it re-stratified all intermediate risk patients into a high risk and a low risk group. So it reassigned intermediate RISS patients to high risk or low risk groups. And by doing this, the two cluster classification outperformed the ISS and the revised ISS score. And what did the model look at was the high-risk cytogenetics and raised LDH. All these intermediate risk patients with high-risk cytogenetics or raised LDH were assigned to the high-risk group, and still 15 to 30% of the patients in the intermediate revised ISS group were assigned to the high-risk group, regardless of the cytogenetics and the LDH. And these were patients with advanced urea stage or even with very low hemoglobin. So, and these patients did perform poorly too. We analyzed them separately, and they did perform very poorly. So there is evidence that prognostication with simple information, with simple variables, can also be improved with machine learning tools, and we expect to reproduce these with external data from larger cooperative groups, so we can do and improve prognostication of myeloma patients also with simple information that's available for all, also for patients in the developing countries. So a lot of interest exists for this in the pharma companies, as you can see in this slide. It's self-explanatory, but we need to implement also these strategies also in academic research, not just in industry research, to keep the pace with their development. And my personal perspective is that machine learning is progressively becoming a new tool for optimizing information in myeloma and in all hematology. And the next generation of prognostic scores will be AI-driven, that the next generation of clinical trials will have AI-based analysis and possibly also AI-based patient populations for selected patient populations. Also, that the next generation of drugs will be designed and optimized with AI. We are actually working in this field. And also that real-world evidence will be used not just to confirm treatment efficacy, but to develop and validate these predictive models. This will not only happen in myeloma, but across all medical fields, so we have to be prepared also as clinicians. And thanks to all the people we collaborate with, particularly Mariby Mateos and Dra. Gonzalez from my team, Santiago Compostela, and also Senem Barro, who is the guy from the machine learning department of our university. So thank you, and sorry for my exceeding time.